Welcome back. So today we're going to talk about how to solve a graph problem on a GPU. And so this is the problem of breadth first search. So before we get started, I want to mention that, so just like the problem we talked about last time, which is sparse matrix vector multiply, right? So breadth first search also is not a problem which is ideally suited to GPUs. Okay, so it's not a very regular problem, just like SPMV. Okay. However, just like SPMV, it's also it's an important problem which has many applications, and also by finding the right algorithm and the right optimizations for the GPU, we can actually get good performance for BFS on the GPU, right? Um, okay, so just to remind you what the BFS problem is, right? It's basically you want to take a graph and you want to explore this graph and do it layer by layer, okay? And so in this example, right, so suppose you start at a node S over here, right? So then in BFS, you first want to find the neighbors of S, okay? So those are all these black nodes, right? The ones labeled by 1. So they're just one hop away from S, right? And the next, you want to find the 2-hop neighbors of S, right? So these are the neighbors of the black nodes, right, which are different from S, right? So those are the gray nodes marked by 2, okay, and so on. And then you can also represent these nodes using a tree, right, like you're doing on the right. So that is the BFS tree. Okay, so so this BFS actually has a large number of applications. So for example, if we're given a graph, and the graph can represent many different things. For example, it can be like a social network and represent friends or something, right? One thing you want to do is to find the connected components, right? Like who do I know through all of my friends, okay? You can also do things like pathfinding using BFS, okay? BFS is used as a subroutine in many other algorithms like max flow algorithms. Now this thing, the Cuthill-McKee ordering, okay? So this was, remember from the SPMV lecture, we talked about a way to reorder a matrix so that you can get more regularity in the matrix, right? So you can start with the matrix on the right over here, right, which is looks like a completely garbled type of thing. And then if you reorder these rows and columns, you can actually get something which looks much more ordered, right? And then now you can apply one of these nice matrix formats like the diagonal format for this matrix, okay? And one of the methods for reordering matrices is the Cuthill-McKee ordering, right? And this is basically based on doing a BFS, okay? Yeah, so that's another application for BFS, and there are many, many applications for BFS, okay? BFS is also used in benchmarks to gauge the performance of computers, okay, like supercomputers. So for example, we have something called the Graph 500 benchmark, which is basically the top 500 supercomputers, but now not ranked by LIMPAC, but instead ranked by their performance on basically BFS, okay? And then you have other benchmarks that also test BFS, and these benchmarks are basically stressing the memory performance of a computer, right? So they're testing how good your memory system is, because BFS requires you to do things like make a lot of random memory accesses. Okay, so this stresses the memory system. There's very little computation in BFS. Okay, so what kind of graphs do we want to deal with in BFS? So typically we want to deal with these large real-world graphs. Okay, so for example, I've listed a few of them, and you can kind of look at the picture in the second column to get some idea what they look like. Okay, so for example, this the first map over here, right? This actually represents the road network of different European countries. Okay, so so let's see if I can zoom in here. Yeah, so if you zoom in over here, you can kind of see these block structures. Okay, so the block structures basically represent different countries and the road network within a country, because you're going to have a denser road network within a country than across different countries, right? So maybe, for example, this biggest square over here, right? This might be the road network inside like Germany or something, right? and then the next one might be like France, right, and then maybe like England or Italy or something like that. Okay, right. So this is a large network. So in fact, it's got 51 million nodes. Okay, so I guess each intersection of the roads is maybe a node, right? So it's got 51 million of those, right? And it's got about 110 million edges. Okay, so I guess between two intersections you have one road, right? And so and then you have two directions, right? You have at each intersection you have two roads crossing there. So basically you have like twice as many edges as you have nodes. Okay, so the average degree is like 2.1. Right, and also the search depth over here. Okay, so this is referring to like if you start at some location, some intersection. Okay, now how many intersections can you go through? What is the farthest sort of the farthest location in terms of the number of roads that you have to travel through? Okay, so so apparently it takes you about like 19,000 roads to get from maybe one side of Europe to another. Okay. All right, so then, but then you have graphs which are very different from this road network, right? So this road network is somewhat dense. Actually, it's not, I guess. But anyways, it's got this structure, right? It's got this hierarchical structure. Whereas if you go for the grid 5-point thing, so this has this definitely does not have this hierarchical structure. It's basically like you have I think 5 diagonal elements. Okay, so here you can only see one of them because of the resolution. So this also has like about 25 million nodes, right? 125 million edges, right? And the search depth here is going to be 7,500. Okay. Now, so these have relatively large diameters. Okay. In order to go from one side of the network to the other, you have to go through many edges. But you also have graphs which are very large, but they have small diameters. Okay. So for example, here you have a graph representing Wikipedia, right? The connectivity between different Wikipedia pages, and you have 3.6 million pages, and then on average each page is connected to 12.6 other pages. But to get from any page to another only takes you 20 links. Okay, so you can basically hop from any Wikipedia article to any other one by clicking 20 times. Okay, so that's kind of interesting. And then you have you have graphs with even smaller diameters. Okay, so these last 3 graphs are kind of like they're synthetic graphs, right? They're generated by some sort of random process. Okay, so in general, we're going to be working with these large graphs that have millions and millions of nodes and edges. Okay, now in practice, you could encounter even larger graphs that have billions or trillions of edges, but the problem is that you can't fit these into the memory of a single GPU. Okay, so one of the weaknesses of GPUs is that they have limited memory. Okay, okay. So the other thing to observe about these real-world graphs is that they have, on average, low degree. Right, so the degree is shown over here. That's like the average number of non-zeros in these matrices per row. Okay, so you can see that even if you have millions of rows, right, on average or millions of columns, on average each row only has like 80, or maybe in this case it's only got 2 non-zero columns. Okay, and at most it's got like 80 non-zero columns, or 96 rather. Okay, however, there's a huge variation in the number of non-zeros per row. Okay, so for example, in this Wikipedia thing, right, on average, each article has 12 neighbors. Okay, 12 links. Okay, but you could have some articles that just have 1 link, right? And whereas other articles could have like hundreds or thousands of links. Okay, so so the degree of different nodes is going to be very different in these real-world graphs. Okay, and then you have these 2 different types of graphs, which one type has like low diameter, right? So on the order of a few dozen or something. And then you also have other nodes which are more like grids, right? Which have high diameter, like the European road network, right? It's got high diameter. Yeah. Okay, and I should mention that all of these this content is basically coming out of this paper called this, right, written by these NVIDIA guys, Merrill Garland and Grimshaw. Okay, so this is one of the earliest papers on doing efficient BFS in GPUs. Okay, it's got lots of great ideas in there, and basically stuff I'm saying today comes from that paper. Okay, and this paper is also the basis for many other follow-up BFS works follow-ups. Okay, so BFS on GPUs. So even though people have been doing this for about a decade now, this is still like an interesting area of research because we still don't have the best, most optimal algorithms yet, and so people are still trying to find improved ways of doing this. Okay, given the importance of this problem and given the challenge of actually doing this efficiently on GPUs, this is still an interesting research area. Okay, so first of all, let's sort of recall the sequential algorithm for doing a BFS, okay, which is going to be the starting point for our parallel GPU algorithm for doing BFS. Since we're assuming the graphs are sparse, we're going to store them in the compressed sparse row format, the CSR format. Okay, so the CSR format, remember from the SPMV lecture, this is some way of storing a sparse matrix or a graph, right? So the matrix and the graph are kind of they correspond to each other. Okay, so the way this works is that let's look at this this example graph over here. Okay, so this graph has 8 nodes in it. Okay, so this R vector here is basically, so the C vector is giving the connectivity of the different nodes. Okay, and there are apparently there are 11 edges in total in this graph. Okay, 11 directed edges, and the R vector over here is showing where do the connectivity patterns for different nodes start. So we have 8 nodes over here. So for example, this the fact that R1 equals 2 means that if you want to figure out the connections for node 1, right, then you should go to index 2. Okay, so this is pointing over here. And if you look over here, what this is going to say is that, okay, so since we're looking at R1, right, this is giving us the connectivity for node 1. And node 1 is connected to 0, right, and to 2, and to 4. And so that's why you have 0, 2, 4 over here. Okay, so if you look at some other one, if you look at node 4, okay, node 4 is connected to in order to find its connectivity information, you jump to index 6 over here, right? And you see that it's connected to 5 and 7, right? So 4 is connected to 5 and to 7. Okay, so we store the graph in this CSR format. Okay, and now the algorithm to do a BFS is we're going to use a queue. Okay, the queue is going to keep track of the unvisited nodes in the BFS. And what we're going to do is we keep taking a node from the top of the queue, right, from the front of the queue, and then we look at which neighbors it has not visited yet, right, and then we add those to the back of the queue. Okay, so the algorithm would be something like what we have on the right. So so these distance things are keeping track of how many hops does it take to get to different nodes. Okay, so initially we can't get to any node, so we assume their distances are all infinite, except for the source node, right? So we start at the source node, so his distance is 0. We put him in the queue, right? So this is the queue, and then we keep taking things out of the queue, right? You decode something, dequeue something out of the queue, and then this thing over here, right? This for loop is going to be looking at the neighbors of all of these of this node I. Okay, so the way you get that is you go to the ith location in this R array, right? And the neighbors of I are located between indices R of I and R of I plus 1 minus 1, right? They're located between these indices in the C array. Okay, so we go to the C array and we look at all of these offsets, and then for each of these nodes, neighbors of I, right? If it's still unvisited, so its distance will be infinite if it's unvisited. Okay, then we set its distance to be the distance of I plus 1. okay, because we can get to node I through through this number of hops, and so that thing plus 1, that number of hops we can get to node J. And then you add J into the queue. And then you keep doing this until your queue becomes empty. Okay, and then you can show that this is going to visit every edge basically once, and so so your running time is going to be order v plus e, where v is the number of edges, sorry, v is the number of vertices, and e is the number of edges. Okay, and then if you do this, then this is what you're going to get. Okay, when you execute from node 0. Okay, so so now let's look at a parallel version of this algorithm. Okay, so that was the sequential version. For the parallel version, let's see. Okay, so the first parallel version, so there were attempts at doing BFS before the Merrill paper. Okay. However, those attempts basically focused on making use of the large computational power of the GPU and completely focused on data parallelism. Okay. So and those algorithms were not efficient, and so they ran quite slowly. And so I'll show you what efficient means. But basically, the way that work is that they're going to start at a source node and set the distance of that node to be 0. Right. So they start at the source node over here, and then they're going to run for d number of rounds. Okay, where d is the diameter of this entire network. Okay, so the diameter is that if you start at the source node, right, and then you look at any other node, and you look at how many hops it gets to that other, it takes to get to that other node, right? Now, what is the farthest node, right? What is the maximum number of hops it takes to get to any node, right? That's the diameter. Okay, so it's the maximum distance that you end up with in the BFS calculation. And these early papers on BFS for GPUs, okay, they ran for order D. They ran for D rounds, okay, where D is the diameter, okay. And basically, in round I, you're going to identify all of the nodes which are at distance I, okay. And then to do that, it actually iterates through all of the nodes in the graph, okay. Including the ones that have already been visited. Okay, so you iterate through all of the nodes, and if the node has been marked, right, then that means that it's already been visited, and now you mark its unvisited neighbors, okay, and as having distance I plus 1. Okay, so looking inside this code over here, right, so here's where you iterate through all of the nodes. Okay, for all the nodes in this node set V. Right, you look at okay, is this node the distance of this node, is it equal to the current iteration? Okay, so we run for d iterations, right? So in the in this iteration, right, we're trying to find all of the nodes at this distance, and then we look for their neighbors. Okay, so therefore, if the distance of a node is equal to this iteration thing, right, then we're going to go look for all of the neighbors of this node. Right, and then we're going to set their distance. As long as they have not been visited yet, we're going to set their distance to be iteration plus 1. Okay, so there's a little bug in this code. So we should actually add this line that if the node has not been visited. Okay, so if its current distance is infinite, then we're going to set its distance to be the current iteration plus 1. Okay, and then after you've done this for all of the nodes in the graph, right, then you go to the next iteration. Okay, the next larger distance. Okay, so now, so basically the complexity of this algorithm is going to be v times e. Okay, because the diameter can potentially be up to order v, right? Because the only upper bound you really have on the diameter is that it can't be more than the number of nodes. Okay, and in each round, right, each of these iterations of the, let's see, where is it? In each iteration of the while loop, okay, you could potentially visit all of the edges. So therefore, the overall running time, the upper bound, is going to be order v times e, okay? And in general, this is going to work okay. It works okay for small diameter graphs, okay? Because for small diameters, you're not going to be running this while loop for that many iterations. Okay, if your diameter is like 10, you're only going to run this for 10 iterations. Okay. However, as we saw with the previous chart, you sometimes have graphs with very large diameters. Okay, like the road network had a diameter of like 20,000. Okay, so then you would need to iterate 20,000 times through all of the nodes if you run this algorithm. Okay, so it's inefficient for those large diameter graphs. So what we want is a more efficient way of doing BFS. And so we're going to look for this approach that does the same amount of work as the sequential algorithm. So the sequential algorithm does linear work, right? Order v plus e, not v times e. So now we want to look for a parallel algorithm which can do the same total amount of work. Okay, and the way it's gonna so to start out with, we're gonna simply adapt the sequential algorithm to sort of work in a parallel setting. Okay, so we're gonna take parts of it and then parallelize it. So for example, one thing that you can parallelize is that, well, initially you need to assign all of the nodes to have infinite weight, right? Because you haven't visited any of them. Okay, so of course you can do that assignment in parallel. Okay, so that's one easy part to do in parallel. Okay, and then you're going to be enqueuing the initial source node. However, now because you have parallel nodes, parallel threads, right? You just want, well, first of all, you don't want to enqueue the source node multiple times. Okay, and also now you have a queue which can be accessed by multiple threads at the same time. So when you access this queue, you need to lock the queue in order to make sure that you don't get any concurrent accesses which can mess up the queue. Okay, if you just allow the threads to access the queue without any synchronization, then you can sort of mess up the queue. Okay, so it can hold incorrect information. So therefore, anytime you want to access the queue in the parallel algorithm, you're going to have to lock it. Okay, so so this is why we do a locked-in queue now. All right, and then we're going to go into this while loop, which is like the while loop for the sequential algorithm, where you keep taking things out of the queue, and then now let's see, for I in the queue, okay, so yeah, so now we're going to take all of the things out of the queue, and we're going to process all of these different items in parallel. All the different items in the queue, we're going to process in parallel. And for each of those items, we're going to find all of those neighbors of this node I. Okay, so for each I in the queue, we're going to find all their neighbors, right? And if the neighbor hasn't been visited, then we're going to enqueue that neighbor into the queue. Okay, however, when you do the enqueue, again, you have to do a locked enqueue. You have to lock the queue first and then do the enqueue. Okay, so now this algorithm is going to work, but there are two big bottlenecks, performance bottlenecks to this. So the first one is that since we're using the queue and we have to lock it, this locking operation is very expensive. Okay, and it's going to take away, it's going to be, it's going to really hurt the parallelism of the algorithm also, because you can only have one thread lock at a time. Okay. And the other problem is that, so since we're processing all of these different nodes in parallel, right? So different nodes have different numbers of neighbors. And the time that you run this for loop for depends on your number of neighbors. Okay, so different threads can run for different, very different amounts of time. So you have a lot of load imbalance in this algorithm. Okay, so then, so next we're going to try to sort of fix these two problems. Okay, we're going to try to not use an explicit queue, right, and then try to find some way to avoid having to lock things. Okay, because that's very expensive. And also, we're going to try to find a better way to load balance between threads. Okay, so so first let's figure out how to avoid using a locked queue or a lock with a queue. Okay, so to do this, we're gonna keep track of two queues. Okay, one queue represents the nodes in the current layer, and then the other queue represents nodes in the next layer. Okay, and then after every iteration, main iteration of the BFS, right? So after we found each layer of the BFS, and we're going on to the next layer, then we simply swap the queues. Okay, and that way we can keep reusing the same memory, right? And then we process each layer in a separate kernel. Okay. All right. So then, for each node in the first queue, okay, we're going to take all its neighbors and add it into its second queue. However, the problem here is that some of these neighbors from the first queue, so some of the nodes, some of the neighbors of the node from the first queue do not actually belong in the next BFS layer. Okay. For example, some nodes have already been visited. Okay, so suppose you have a node over here, right? Suppose you have two visited nodes over here, okay? And they, well, let's see. Yeah, so this guy has been visited, and this guy has been visited, and this guy has not been visited, okay? Right, so then if we're processing this node, right, and if he's got edges to both nodes, right, then we should only add this node into the queue. We shouldn't add this node, okay? Because he's already been visited. And so we need some way to figure out which nodes have been visited or not. Okay. Now it turns out that if we want to test each node and whether it's been visited, okay, it's kind of expensive to do this. So we want to find some more efficient ways of figuring out whether a node has been visited or not. Okay, and I'll show you methods to doing this later. Okay. Another problem is that we might be adding duplicates into the second queue. Okay, to show this, suppose we have a situation where you have nodes, right? Now, suppose this this top node has, well, okay, so suppose it's unvisited, okay? And now you have one thread processing this node, right? And then you have a different thread processing this node. So then both these threads would try to add this unvisited node into the queue, okay? And it would get added twice into the queue. So we would have duplicates. Right, so we could have, in fact, many duplicates if you have more threads that want to add this thread into the queue. Okay, so so we have these two problems. One is that testing whether a node has been visited or not, i.e., whether it belongs in the queue or not, explicitly testing this is inefficient. Okay, the other problem is that we may be adding duplicates into the next layer's queue. And so we'll see how to address these problems later. Okay. But for now, we just want to see how we can be adding things into the queue without using explicit locking. And the way we're going to do this is we're going to use prefix sum again. Okay. So the idea is that suppose each node knows how many neighbors it has, okay, and how many things it wants to add into the queue. Okay. So suppose a node has suppose a node I has n sub I neighbors. Okay, so then it wants to add all of its neighbors into the queue. Then what we're going to do is we're just going to reserve n sub I slots in the queue for this node. Okay, so as an example of this, suppose that the first node wants to has two neighbors, so it wants to add two things into the queue. Okay, the next node has one neighbor, right? Wants to add one thing. The third node doesn't have any neighbors, and the fourth node has three neighbors. Okay, so now we want to reserve enough spaces in the queue for the neighbors of all of these threads. So what we're going to do is we're going to do a prefix sum on the number of locations that each thread needs. Okay, we're going to do an exclusive prefix sum. And the result of the exclusive prefix sum is going to tell you the index so we're going to think of the queue now as just an array, okay? And the result of the prefix sum is going to tell you the index at which each node should be putting its neighbors. Okay, so to make this more concrete, right? If you do exclusive prefix sum on this this array here, 2, 1, 0, 3, right? You're going to get these answers, right? So that means that the first node who wants 2 spots, right? He should start at location 0. Okay, so that's what this 0 means. Right, and then the next node, which wants one spot, he should start at location 2, right? Because the first guy is already reserved 2 locations, so the next guy should start at location 2, right? The third guy should start at location 3, and the fourth guy should start also at location 3 because the third guy doesn't have any neighbors. Okay, so therefore by doing this prefix sum, right, we can figure out exactly which locations in the queue to reserve for each thread. Okay, and now each thread can just go ahead and add its neighbors into those locations. And there will not be any conflicts between these. So we can be doing all of these additions into the these in-queues into the queue in parallel, but there won't be any conflicts now because, for example, thread 0 and thread 1, right, they're in-queuing into completely disjoint locations. Okay, so there's no conflict. Okay, in fact, there's no conflict between any of these threads because they're going to be in-queuing into completely different locations. Okay, and the only thing we needed to do was to do a prefix sum, which we can do in parallel. And then after that, we can do all of the in-queues in parallel also. And we don't need to do any to use any expensive locks. Okay, so this is a way to get rid of locks. Okay, so now that we don't have to use locks anymore, now let's figure out how to do load balancing. Okay, so so basically the idea is that since different nodes have different numbers of neighbors, then we're going to need to assign different numbers of threads to gather the neighbors of different nodes. Okay, so the nodes that have lots of neighbors, you need to assign more threads to process their neighbors. Okay, so so the way we're going to do these allocations of threads is that we're going to say that if a node has a moderate number of neighbors. Okay, so moderate means so it means something, and I'll talk more about that later. But if you have a moderate number of neighbors, okay, then we're going to assign a warp of threads, warp of 32 threads, to help gather the neighbors of this node. Okay, the problem is that you have these 32 threads. And initially, they might all be trying to process different nodes, okay? But now, since you found a node with a moderate number of neighbors, now you don't want these threads to process different nodes. You want them all to focus on one node and to cooperate on getting the neighbors of this one node, okay? So how do you get these threads, which initially are working on different things, to come together and work on a single node? So what they're going to do, what we're going to do is have the warp of threads vote to find a single node to work on. Okay, and the way that the threads are going to vote is that they're going to write to a common memory location, right, and then read it. Okay, so for example, you write you write your ID to a common memory location, and then you read that common memory location. Okay, now one of those writes is going to happen last, and so therefore the final value at that read location is going to be whichever write happens last. Okay, so like if you have 32 threads, they have IDs 0 to 31. Okay, so then they're going to write to a common memory location, and if it turns out that thread number 18, right, was the last one to write, then the final value of that memory location is going to be 18. And so that means that 18 wins the vote. Okay, so that means that whichever node 18 wanted to process, right, this entire warp has to go help 18. Okay, they can't do their own nodes anymore. They have to, because 18 won the vote, they all have to go help 18, gather the neighbors of 18's node. Okay, so that's for a moderate number of neighbors. Is we assign a thread of a warp of threads to help. And if a node has a large number of neighbors, okay, so again, what does large mean? Well, it depends. Okay, it's like a parameter that we have to tune. But if it has a large number of neighbors, then we're going to use an entire block of threads to help with the gather. Like if you have like thousands and thousands of neighbors, okay, then maybe we want to assign like several hundred threads to help you get your neighbors. Okay, and then for the remaining nodes that have just a small number of neighbors, then we're just going to do like a simple, then each of them is just going to gather their own neighbors. Okay, like if you have 3 neighbors, okay, we're not going to assign a warp to help you out. You're just going to get your own 3 neighbors. And then you're going to use the prefix sum method to say that I have 3 neighbors, right? Give me 3 locations in the queue. Okay. So there is going to be some load imbalance, right? We haven't. So this method does not completely remove all load imbalance. Okay. However, it is better than just assigning 1 thread for every node. Okay, because in that case, you can get humongous load imbalance, right? If one thread has like 10,000 neighbors and another thread has 1 neighbor, that's tremendous load imbalance. Okay, so here instead, we're going to have some load imbalance, but it's not going to be as severe. Okay, now the actual size of moderate and large. Okay, so this needs to be tuned for the implementation, right? Yeah, so there's no predefined figure, but you can imagine that if you assign a warp of 32 threads, the moderate kind of means maybe up to a few hundred neighbors. We're gonna process them using a warp of threads. Okay, whereas if you have many thousands of neighbors, right, then that's gonna be a large number of neighbors, and we use a block of threads for doing that. Okay, so it's not a perfect solution, but it's helpful. Okay, so next we need to look at before you add a node into the queue, you should know whether it's been visited or not, right? For the next layer, right? Yeah, so you need to know whether it's been visited or not. So one way to do that is you can just have a flag for the node indicating whether it's been visited. Okay. However, if you have a flag for every node indicating its visitation status, then that's going to cause quite a bit of memory traffic to look up those flags. Okay, because every time you process a node, right? Like if I'm a node and I'm trying to add my neighbors, okay, for every one of my neighbors, I need to go look up its visitation status. And if that's stored in a flag, then I need to do a memory access just for that flag. So we kind of want to reduce this memory traffic. Okay, so what we're going to do is, in fact, we're going to use an integer to store the status of 32 nodes at the same time, because the status is just whether you've been visited or not. So that's just a single bit, right? So if we have an integer, then we can actually use that to store 32 visited statuses within the single integer. Okay, so the integer is going to be a bit mask. Okay, but the problem is that now, since we're modifying these visited status bit masks, we're modifying them in parallel. Okay, then the different parallel accesses can actually clobber each other, so they can interfere with each other. Okay, so as an example of this, suppose you have suppose we have just 4 bits. Okay, so suppose 4 bits are in the integer, right? And now we want to change the visited status of some nodes. Okay, so let's say that we one thread is going to visit this node, and another thread is going to visit that node. So the first thread wants to change this to so the first thread is going to read the visited status of all the nodes, right? It sees that none of these nodes have been visited, and so it wants to indicate that it has visited the second node. So it's going to change the visited bit mask to this, okay, to 0100. Okay. Now, concurrent to that, you have, let's say, another thread which is visiting the third node. Okay, so it also read this visited status, and it just wants to mark the third bit as 1. Okay, so then now you have this situation, and now both of them are going to write to the are going to write their new bit mask back to this bit mask location. Okay, and now it just depends on whose write happens last. Okay, so for example, if the guy on the right, if his write happened last, then the final bit flag array is going to end up as this. Okay, so basically that means that the visited status for for node 2 didn't change. Okay, it got overwritten. Okay, and this is because you had two threads running concurrently. Okay, now if the 2 threads were not running concurrently, right? If the first thread completely finished, right? So let's say you have a different situation where the first thread completely finished, right? And then it read this, right? It changed it to 0100, and then you have the other thread come, okay? Then the other thread is going to read 0100, and it's going to change it to 0110. Okay, so that's not a problem. Okay, so the problem comes when you have multiple threads reading this concurrently. Now, one way that you can avoid this situation is you can use these intrinsic atomic operations, right? You can sort of do the get and set operation, for example. Okay, and that would avoid these problems. However, the atomic operations are kind of slow. Okay, so in this paper, they wanted to avoid using atomic operations. Okay, so instead, they just use these normal read and write operations. Okay, and when you do that, you could get these problems. Okay, you could get the clobbering problem. Okay, 0100 and then 0010. Okay. However, they're going to treat the way they deal with this is that they treat the bit mask conservatively. Okay, so suppose you have the situation and the final state ends up being 0, 0, 1, 0. Okay, now if you want to know whether this node has been visited, you check its visited status. Okay, so if it's 1, then that means that it's definitely been visited. Okay, because if it's 1, then somebody must have written that 1, and so that node, so this thread visited that node. So whenever you see a 1 bit, you can be guaranteed that the node has been visited. Okay. However, let's see. Right. So if the bit for a node is set, it's definitely visited. Okay. But if it's not set, right? So for example, if you read this bit, right, and you get 0, right, that doesn't necessarily mean that the node has not been visited, right? It could have been overwritten. Okay. So therefore, if it's 0, then we're going to have another label, right, which is going to be the visited status for this node. Okay, so every node is both going to have a completely different. We're going to have a completely different integer flag for every node. Okay, and we're also going to have these 32-bit bit masks for keeping track of the nodes. And we're going to read the bit mask first. Okay, if we see a 1 there, then we know the node has been visited, and we're done. If we see a 0, then we cannot be sure the node has not been visited. And so therefore, we're going to go to this private label for the node to check whether it has really been visited or not. Okay. Now, these private labels are not going to have this, clobbering problem, right? Because every node has a different label, and so so they're not going to overwrite each other. Okay, but the nice thing about having both the bit mask and the labels is that usually we're checking the bit mask first, right? And as long as the bit mask says 1, then we don't need to check the label. Okay, and only when it says 0 do we need to check the label. Okay, so usually we're only checking the bit mask. And it's much more efficient to check the bit mask because it's got 32 pieces of information, in the same integer. Okay, compared to the label, which only has information for 1 node in the integer. Okay, so the idea is that usually we're going to save by doing this. Okay, and so in this paper they did some experiments to see how effective this having this mechanism of both the bit masks and the labels is. Okay, so the bit masks were cached in the GPU's texture cache, and it turned out that their bit mask system, this method, was effective for low diameter graphs. Okay, and for high diameter graphs, it didn't work as well. So one of the reasons is that each layer of the BFS, okay, was processed in a separate kernel, and each time you start a new kernel, you flush the cache. So therefore, since the bit masks were cached, right, and you kept flushing this cache, it didn't work that well. And it also didn't work well when you have these small frontiers. So frontier is like the how big your next BFS layer is. Okay, because if you have a small frontier, then the cache values aren't reused too much. Okay, so they did some experiments on different types of graphs, right? So the x-axis here represents different types of graphs, and they compared the amount of memory traffic for each edge using either just the label lookup, where you just have a label indicating the visited status of a node. Okay, you don't use the bit mask. Okay, or you use the bit mask plus the label lookup. So then you go to the bit mask first, right? And if it says 0, then you have to go to the label also. Okay, so they compare these two methods. So for some graphs, right? So for the high diameter ones, okay. So usually, these graphs are kind of ordered by order of their diameter. Okay, so these are sort of in order of decreasing diameter. Okay, so for example, the map graph had very high diameter, and it turned out that using both a bit mask plus a label was actually worse. Okay, so it incurred like twice as much memory traffic. Okay, and the same thing for other high diameter graphs. But as you move to low diameter graphs, then this method of using both a bit mask and a label becomes more useful. So for example, for for some of these graphs, right, you actually incur like 3-4 times as much memory traffic per edge using just the labels. Okay, and on average, it turned out that using just the labels was going to be about twice as bad as using bitmask plus label. Okay, so in general, it pays to have both the bitmask and the label. It's a good idea. Okay, so this is how you can make looking up the visited status more efficient. So the next thing is we have this issue about duplicates in the frontier, in the next layer of the BFS. Okay, and to give a concrete example how this can happen, so suppose you have in the first iteration you just have a single node 0 over here. Okay, so then its frontier, its next layer, is going to be nodes 1 and 3. Okay, now once you have nodes 1 and 3, right, then if you don't synchronize between these threads, and then you just have them add all of their neighbors into the third layer. Okay, so this is the first layer, right? This is the second layer, right? And now once we have the second layer, we're processing the third layer. We're trying to form the third layer. And if you don't do anything, and you just have all the nodes from the second layer add all of their unvisited neighbors, okay, then what's going to happen is you're going to add 2, right? 2 is a neighbor of 1. It's not visited, right? And 1 is also going to add 4, okay? But 3 is also going to add 4, right? And then 3 is going to add 6. Okay, so if you don't synchronize between 1 and 3, right, then you're going to be adding 4 twice. Okay, so that shows that this frontier is going to have 2 copies of 4. Okay, now let's just say that you continue from this process. Okay, so you have 2 copies of 4, and now let's say that you assign different threads to process this. Okay, so you don't try to get rid of the duplicates. Okay, you just accept that you have 2 copies of 4. Okay, and you assign different threads to all 4 nodes. Then what's going to happen is that now you're going to be adding the neighbors of the third layer, right? So 6 is going to add 7, right? 4 is going to add 7, right? But you also have this other copy of 4 that's also going to add a second 7. Okay, and then the 4 is going to add the 5, and the other 4 is also going to add the 5, and the 2 is going to add the 5. Okay, so now you have like 3 copies of 5 and 3 copies of 7. Okay, and finally, if you just assign threads to all of these nodes, right, including the duplicates, then you're going to end up with like what is it, like 7 copies of 8. Okay, yeah. So or I guess 6 copies. I don't know why they're showing 7, but anyways, but you're going to have more and more duplicates as you go on. Okay. And this issue about having duplicates is actually more problematic in the GPU, okay? Because the GPU is SIMD, so unless you do some sort of duplicate removal, okay? If you don't do duplicate removal, then because the GPU is SIMD, and because you have many parallel threads, then you could really potentially assign different threads to all of these nodes, and there could be duplicates within these nodes. And that's going to cause even more duplicates in the next layer, which is going to cause even more duplicates. Okay, so the number of duplicates can actually grow, can blow up exponentially. Okay, so these guys, the authors of the paper, they did some experiments on how big of a problem this duplicate issue is. Okay, so what they compared was that, so for different graphs, they looked at different iterations of the graph. Okay, so remember that the duplicates actually can grow with the number of iterations. Okay, and so they looked at 3 different measures. So the first measure is the size of the edge frontier. And this is just where you look at the number of nodes in the next layer, and then you allow duplicates. Okay, so you don't do anything about duplicates. So next, they looked at unique neighbors, okay, which is that you allow duplicates, you get rid of duplicates, but you allow visited nodes. Okay, then how many nodes would you have? Okay, and finally, the what you actually want is you want this thing called the vertex frontier, which is that you want the you don't want any duplicate neighbors, right? And then you also don't want any visited nodes. Okay, so this is what you actually want. And now, if you look at different graphs, okay, so let's maybe look at this graph. It's the clearest one. Okay, so we're going to look at different iterations of the BFS. Okay, so this one runs for 800 iterations. So that basically means that this graph has a diameter of like 800 or something. And you can see that if you allow duplicates, okay, and visited nodes, you're going to get so this top thing, right, the black curve, okay, that's where you allow all of these bad things to happen. You allow duplicates and visited nodes. Okay, so the gray one, right, the dark gray is going to be where you get rid of the duplicates, but you still allow these visited nodes, which you don't want. Okay, so and then the light gray is going to be the correct answer. So you can see that when you allow duplicates and visited nodes, you're going to get a lot of extra nodes. Okay, a lot of extra incorrect nodes that you want to take out later. Okay, if you only allow these previously visited nodes, you still get some sort of redundancy. Okay. And this is for this graph over here, this grid 7-point graph, but it's not extremely severe in this graph. But if you look in some other graphs, you can see that the problem is actually very severe. Okay, so for example, if you look at this NLPK graph, right, you can see that when you allow duplicates, right, you have this number of nodes. Okay, you have, what is this, like 4 million nodes. Okay, in the final iteration. Whereas if you take out the duplicates, you have something, you have less than you have less than 500,000 nodes. Okay, so this is causing a huge number of duplicates in certain graphs. Okay, so one of the contributions of this paper was to have some way of removing the duplicates, have an efficient way of removing the duplicates, and when you do that, your algorithm can run much faster, right? Because if you don't remove the duplicates, then you have all of this redundant work being done. Right, you process 3 times. Okay, you do 3 times as much work as necessary. Okay, whereas if you take out all the duplicates, right, then you just have two nodes to process. Okay, so then they call this process a duplicate culling. Okay, so they're gonna cull or remove all of these duplicates, and the way they do this is using a hash table. Okay, now the hash table is not going to remove all of the duplicates, but it's quite effective. Okay, so if previously you had like 10 duplicates, okay, then it might get rid of like 9 of them. Okay, so you still have a few duplicates, but it's much better than before. And they have different ways of implementing this culling. So the first way is using warp culling. Okay, so here every warp is going to create a hash table, let's say with 128 entries in the shared memory. Okay, and then when you insert a new node, you want to figure out whether this new node is a duplicate or not. Okay, so therefore you're going to hash it to some location in your hash table, and if it's currently empty, if that location is empty, then this is definitely not a duplicate yet, right? Because this means that you have not inserted this node into the you've not visited this node before, or sorry, you've not inserted this node into the queue before. Okay, so if the table entry is empty, then you simply store it in the table entry. Okay, and you also add this node to the queue because you're sure it's not been added to the queue yet. But if the table entry is filled, okay, then you're going to check whether so then the table entry is going to store which node has already been added to it. Okay, so you're going to check whether that entry equals your current node. Okay, and if it equals your current node, right, then you know that this node has already been added to the queue. So in that case, you don't add it to the queue. Okay, and otherwise, if the entry is not equal to your current node, okay, then what happened is that you have 2 different nodes which happen to hash to the same location. Okay, now you aren't sure whether your node has already been added yet, right? Because the current table entry is storing the information for a different node. Okay, so you know that different node has already been added to the queue, but you don't know whether your node has been added to the queue. Okay, so in that case, to be safe, we're going to add our node to the queue. Okay, because maybe it's not in the queue yet. So that's the warp culling method. Okay, where each warp has its own hash table. And the history culling method is basically the same idea, except for you're not going to put the hash table in the shared memory. You're going to use the SM's L1 cache to do the culling process. Okay, and then the entire block of threads is going to share that L1 cache. Okay, so the warp culling is sort of culling based per warp hash table, and then the history culling is going to be a per block hash table. Okay, and it turns out that even though the hash tables are quite small, right? So the warp culling, you only have 128 entries, and then for the history culling, you have the L1 cache, which is quite small, right? So that can store maybe like a few thousand elements. But it turns out that despite the small sizes of these hash tables, this is still quite effective. Okay, so this is showing that log. Okay. Is this actually the log? Okay, so this is showing the amount of redundancy if you don't do history culling. Sorry, if you don't do any type of culling. Okay, so let's see. Now this is this grid 5 point. Okay, so I'm not sure whether these values are just normal values. Oh, I guess this is a log. Yeah, okay, so we should just read these as normal values, okay? So this is showing that for the European road network, right? If you don't do culling, you're gonna get 1.1 times. You're gonna get like 10% redundancy, right? So it's 1.1 times what you get if you do the culling. If you do the culling, okay? Now you get even better improvement apparently on this grid 5 point graph. Okay, so if you don't do the culling, right, if you just do the simple method, right, then you're going to get 4 times as many nodes as necessary, right? Whereas if you do the culling, you're going to remove that. Okay, so in general, it's showing that the effectiveness of this culling method is different on different graphs. Okay, but if you average everything, then it turns out that you can get rid of like 30% of duplicates using this culling method. Okay. And here, this graph over here, I guess, is showing that you can actually combine all of these different methods. Okay, so you can also you can use a bit mask also. The bit mask and label method, right? So that was for the visited status, but you can actually use this method also to check whether you've added duplicates into your queue. Okay. And furthermore, you can add on top of that, you can add the hash table, the per warp hash table, or you can add the per block hash table. Okay, so what this is showing is that if you, as you add more and more of these methods, right, you're going to be removing more and more of these unnecessary duplicate nodes. Okay, yeah, so. Right, and then the effectiveness overall is going to be, this is like the average effectiveness of these methods. Okay, so now we're going to combine all of these methods. Okay, so now we've looked at how to not use a lock when we're processing the queue, right? We looked at how to determine the visited status of nodes, and we looked at how to remove duplicates. Okay, so now we're going to put all these elements together, and we're going to build our BFS algorithm. Okay, so the algorithm is, as we said previously, each layer of the kernel, each layer of the BFS is going to be computed in one kernel. Okay, so if you have 100 layers, you need to run 100 kernels. You need to start 100 kernels. Okay, and the input to this kernel. Okay, so we're trying to compute one layer, and our input is a previous layer. Okay, and the previous layer might actually have duplicate nodes in it. Okay, and now we're going to take our threads for the current kernel and assign them to the input queue, right? The previous BFS layer. Okay, and then the thread is first of all going to use either warp or history culling, or maybe both, to determine whether it's the vertex it's been assigned, right? So each thread is assigned some vertices, and it's going to determine whether each of its assigned vertices is a duplicate or not. Okay, if it's not a duplicate, right, then the thread is going to go ahead and gather the node's neighbors, right? It's going to try to take the node's neighbors and then add them into the into this layer's queue. Okay, and then based on how many neighbors we have, right, we're either going to use a block or a warp or just the thread itself to collect these neighbors. right? So if the thread has many, many neighbors, we're going to have an entire, this thread is going to try to grab an entire block of threads to help it read the neighbors. Okay, if the thread just has a few neighbors, right, like 2 neighbors, it's just going to grab the neighbors themselves, itself, okay, by itself. Okay, so yeah, so here this is just saying that, right? So initially each thread might want to process a different node, right? But if it turns out that if a thread sees that it has a huge number of neighbors, it's going to try to enlist additional threads to help it collect these neighbors, okay? Either a block or a warp of threads, depending on how many neighbors it has, okay? And it does that by writing to a shared variable and then reading from the variable, okay? And then whoever is the last to write, that guy wins, and all of the remaining threads in the warp or the block has to go help that thread. Okay, and then now now we're starting to actually collect these neighbors and add them into the queue, right? But before doing that, we need to check if it's already been visited. Okay, so if it has been visited, right, and we can determine that using both the bit mask, or if the bit mask says 0, then we're going to check the label, right? So that way we can guarantee that we're not going to add previously visited nodes to the queue. Okay, so if we figure out that our node that we're currently processing, right, our neighbor that we're currently trying to add into the queue, if it has not been visited yet, then we want to reserve one spot in the queue for that neighbor. Okay, so to do that, the thread is going to contribute 1 to the to a prefix sum. Right. So remember the prefix sum, for each value that you put into the prefix sum, you get 1 location in the queue. Okay, so now we found an unvisited neighbor, so we're going to add 1 to the prefix sum to get that guy a location. Okay, and then we're going to do async threads across the entire block of threads, right? And then we're going to do a prefix sum on this entire block to get to find out how many locations this entire block of threads has reserved for its neighbors. Okay, and then we're going to pick one thread in the block to take. So after we compute how many total spots we need, right, for this entire block of threads, then we're going to take one thread, and that thread is going to write to a global global value, which is keeping track of the global queue's size, right? So for example, if this block wants to reserve like 2,000 locations for its neighbors, okay, then we're going to have one thread in the block write increment the global queue size by 2,000. So that's going to reserve 2,000 locations in the global queue for the neighbors of this thread block. Okay, and then it's gonna take the old value of the queue size and return that to the thread block. So now the thread block knows where to start writing in the queue. Yeah, so this is the offset for our prefix sum, and then each thread can now know like where the queue starts, and it can also know its locations within the queue, right? And we're guaranteed that different threads have non-overlapping locations. And so now the threads can just start writing in parallel, can start writing their neighbors into these locations in parallel, and there's no conflict. Okay, so then after we put all this stuff together, we can look at the performance. So now the previous method was actually called the contract expand method, okay? Because it first takes the current layer's edge frontier, right? And then it removes all of the duplicates, okay? So it contracts it. And then it expands into the next layer's frontier, okay? And the next layer's frontier can actually contain duplicates. You can do this in the reverse order, so you can do expand contract, okay? So, so this is going to expand the current vertex frontier and then contract it to remove the duplicates to get the next layer's frontier. Okay, yeah, right. And then there's also something called, so all of these proposals are from this paper, right, from the Merrill paper, okay? And then there's also something called two-phase, which is going to do the expansion and the contraction in 2 different kernels, Okay, so previously you could do the contract and the expand in one kernel, but you can also do them in two kernels. And then they have the hybrid method, which is going to combine the contract and expand, which is like one kernel, with the two-phase, which is like two kernels. Okay, and then they're going to use the two-phase for iterations with large frontiers. And yeah, so you know there are many variations on these methods, and I'm not going to get into too much detail about these different variations. In fact, I don't know the variations too well. I don't know the details that well. Okay, but the basic idea is what we had on the previous slide, and so you can combine these in various ways. Okay, this contract, expand, or vice versa, or two-phase. Okay, and then you would use them, and they have different performances on different types of graphs. Okay, so as you can see from this chart over here, right, different methods are going to work differently on different graphs. Okay, and so they differ in the amount of like memory traffic and latency and parallelism that they have. Okay, and they say that the performance of the hybrid algorithm is mostly determined by the average degree. Okay, so as the average degree let's see, as the average degree, I believe, increases. Okay, yeah, so it increases. So they listed all the graphs over here, right? And as you go down, the average degree tends to increase. Okay, and then the performance actually tends to get, well, it's not monotonic definitely, but it tends to improve as you improve the as you increase the degree, then the speed up that you get. So here they measure the speed up of a GPU compared to an 8-core CPU. Okay, so this is the speed up that you get, and you can see that you're usually getting quite substantial speed up. Okay, so it's definitely worth doing this on a GPU, right? Compared to an even an 8-core CPU, you're getting like 10 times speed up, oftentimes. Okay, up to like 30 times speed up. Okay, yeah. Okay, so this algorithm works quite well. And people are still doing more research on BFS, and they continue to have more and more improved BFS algorithms on the GPU. Okay, so now one way that you can improve the previous algorithm is that maybe you can expand it to multiple GPUs. Okay, so multiple GPUs. Now this paper was written quite a few years ago, and back then multiple GPUs could only communicate through PCI. Okay, and PCI has very limited memory bandwidth, like 6 gigabytes. Okay, so nowadays you have many other ways like of communication between the GPUs. Okay, so for example, you have NVLink, which has hundreds of gigabytes of bandwidth between different GPUs. Okay, but back then they only had PCI, and so they tried to use PCI and have multiple GPUs work together in order to do multi-GPU BFS. So the way they did this was that if you have P GPUs, okay, then you're going to evenly divide the vertices among these GPUs. So each GPU is going to get n divided by P vertices, and it's the total number of vertices. Okay, and then for each vertex, the GPU is also going to get all of the corresponding edges. Okay, and they assign the vertices in round robin order. Okay, so they give so if you have like 4 GPUs, right, they're going to iterate through all of the vertices and give them to GPUs 1, 2, 3, 4, 1, 2, 3, 4, and so on. And they do that for load balancing, but this is going to disrupt the locality of the graph when P is large, because usually the vertices in a graph are organized in some way that if you iterate through the vertices, they tend to be, the neighboring vertices tend to be close to each other. Okay, I mean the vertices don't have to be ordered that way, but usually the way that graphs are formed, they are ordered that way. Okay, so therefore, if you give consecutive vertices to completely different GPUs, then you break the locality between the vertices. Okay, so this is maybe not such a great idea in terms of locality. Okay, and then each GPU is going to run the previous algorithm on its own vertex queue. Okay, just like for what we had before. And then, but now for the new for the next layer, so this is going to form the next layer of the BFS, right? So every GPU is going to form the next layer of the BFS using the vertices that it has in its queue, okay? However, some of these vertices, so remember that different vertices are assigned to different GPUs, right? So if I'm a GPU and I computed my next layer, right, then within my next layer, some of those nodes belong to me, but some of those nodes belong to other GPUs, okay? So therefore, I have to take my next layer and I have to sort them into these P bins, right? Each bin is the vertices that belong to one particular GPU. Okay, and then we're going to synchronize this operation by doing a barrier. And then after that, after I sorted my frontier into these P bins, right, then we're going to have the other CPUs pick out of my bins whichever vertices belong to it. Okay, so that means that we're going to run P-1 kernels, where in the ith kernel, the ith GPU is going to look at every other GPU, and for each of those, it's going to go look in the bin that corresponds to itself. Right, so if I'm the third GPU, I'm going to go look in the third bin of every other GPU, and I'm going to take the vertices from those third bin, which belong to me. Okay, so then after doing that, right, then so after each GPU has done that, right, then each GPU has the vertices that belong to it that are in the next layer. Okay, and so now we can go back to the to this step over here, right? And now we can form the next layer after that. Okay, so we form things layer by layer, but each time we form a layer, right? Every GPU has like a mixture of nodes from different GPUs, right? So we need to make sure that every GPU grabs its own vertices first before we go on to the next layer. Okay, so they tested the performance of this algorithm also. So they tested this on anywhere from 1 to 4 GPUs. Okay, so 1 to 4 GPUs. And then they, so they looked at the performance of this. And you can see that there are some graphs, like for example, this graph, right? You actually get some somewhat better performance as you scale to 4 GPUs, right? You definitely don't get 4 times the performance, but in general, you get better performance. But you still get better performance, okay? However, there are other graphs where you either get no improvement by having more GPUs, right? Or there are even graphs where you get a huge decrease in performance as you go to more GPUs, okay? So for example, on this roadmap graph, right, for the European roadmap, right? So I'm not sure what these numbers are, but it seems like the with 4 GPUs, you're going like much slower than just even having a single GPU. Okay, and the reason is that you have to do all the synchronization between the GPUs, right? Because for each of these layers, right? So each of these layers is being processed in a kernel, and every time you do a layer, right, you have to do this distribution thing of the nodes in the next layer. You have to go distribute those among your GPUs. Okay, so this is very very complicated and time intensive. Okay. So they only managed to achieve speed up on the graphs with small diameters, right? So this graph was one of these random graphs that had a very small diameter and large average degree. Okay, because if you have a small diameter, you don't have to do this node distribution thing too many times, right? You don't have to start too many kernels. You have one kernel per layer of your diameter, and you know for these for graphs like RMAT, you don't have too many layers. Okay, so you don't have too many kernels and too much synchronization. But for the roadmap graph, right? So there you have like 20,000 layers. Okay, so you have to do 20,000. You have to do this synchronization process like 20,000 times. Okay, and that's hugely expensive. Okay, so on average, okay, it was they found that it was not worth it to do to do the to use multiple GPUs. Okay, so on average, you actually perform worse when you use multiple GPUs. Okay, and so that's all we have for this lecture. And so next time, so we're done with the GPU part of the course. And so next time we're going to start on some new topics. Okay, so see you guys next time.